logarithmic differentiation. How do you know when to use it? When it says using logarithmic differentiation, derive the following. You guys sometimes skip over words. And you're like, I didn't know to use logarithmic, and then I'm like, oh, you're like, yes, reading. Reading is good. That's all you need. If you have a 1 out of 10, you'd be good. Fine, you have to read it. All right.
What if you don't know how to read those?
Okay. There are two types of logarithmic differentiation situations where you're going to have to use it. One of them is when you have like a really ugly looking quotient rule. So, number one, say I give you f of x equals x plus 3 squared, 4x cubed minus 1, all over 8x squared plus 6x to the half times 7x cubed minus 2 to the 3. So if you went to do this with your normal quotient rule, to get your f prime, you'd actually have to do product rule with chain rules. And to get your g prime, you'd actually have to do product rule with chain rules. And I assume you would just cry and then call it a day.
Pretty much.
But there's this thing called logarithmic differentiation that actually makes our lives better. But we have to use a little bit of log laws from 30. Not the hard ones, just a little bit. So the spotting for what you need to do is this looks like a really ugly quotient, correct? This is one way. So your first step is going to be to ln both sides. Because you can do whatever the heck you want to an equation as long as you do the same thing to both sides. So it's like a balance scale. If you added a rock to one side, you'd have to add the same weight rock to the other side and still be balanced, correct? So same thing with when you're doing logarithmic differentiation, we're going to ln both sides, because as long as I do it to both sides, it's good. So I'm going to go ln f of x equals ln of this big convoluted thing. Okay. So this is where we use product and quotient log rule. So I'm going to remind you a little bit about 30-1. So whenever you were given something like this, we'll come right back, don't worry about it. But if I gave you like log x, y over z squared, let's say, how could I separate these? Log x, what? Plus, because y is in the numerator, log y, and then what? Minus log z squared, and like you said, the 2 could come in front, right? True? We're doing the exact same rules. This is a ln. So what are we going to do? This ln f of x is going to stay ln f of x. This is going to become ln x plus 3 squared plus ln 4x cubed minus 1, both the numerator, minus ln 8x squared plus 6 to the half, minus ln 7x cubed minus 2 to the 3. So anything in the numerator has a plus sign in front of it, anything in the denominator gets a minus sign, right? Just like you were taught in 30-1. And then what was the other thing we did? We took that exponent, we did what to it? Put it in front. So this is going to move here and become a 2. That one doesn't have one. This is going to move here and become a half in front. This is going to move here and become a 3 in front. So now it's in a form that I can actually do ln derivatives. The derivative of ln, what do? You take it, drop it in the denominator, ln e, and then the derivative of it in the numerator, correct? Do I need to write the ln e's on here? No. So we have to do it to the left side too. So the f of x is going to drop to the denominator, correct? And then the derivative of f of x in the numerator, so f prime of x. True? This is time consuming, but it is not hard. Okay? Then same thing here. 2 drops in front, we can write as 2 over 1. And then the x plus 3 goes in the denominator. What's the derivative of x plus 3? 1 goes in the numerator, right? Then plus ln 4x cubed minus 1, 4x cubed minus 1 goes in the denominator, and then 12x squared goes in the numerator. Done. Right? Then minus a half. Its coefficient, it can just sit in front. 8x squared plus 6 in the denominator, and then 16x in the numerator. Minus 3 over 1. 7x cubed minus 2 in the denominator, and then 21x squared in the numerator. What's that? No. All right.
You lost your x.
Yeah.
Attached to
It's an x on a 6, which would be 16x divided plus 6.
Oh. And there's one down here. Okay. So let's simplify that. So we're going to get f prime of x over f of x equals 2 over x plus 3 plus, now some people think they can cancel things off here. This is 4x minus 3. This is a binomial. The top is a monomial. You cannot cross monomials off with binomials. You guys do some illegal cancellations all the time. Nothing can happen here. That's as good as it gets. 12x squared over 4x cubed minus 1. This one I can take a 2 out of. So if I want to, I can go take a 2 out of this. And then I'll be left with 8x plus 3. Right? This one I can take a 2x out. And I'm left with 4x plus 3. This 2 can cancel off that 2. So I would be left with 8x plus 3 in the numerator, all over 2x, 4x plus 3 in the denominator. And then some people are like, oh, 21 and 7, I can cancel. Once again, I repeat, the numerator is a monomial. The denominator is a binomial. You cannot just cancel things off the binomial with the monomial. Monomials cancel monomials. Binomial twins cancel binomial twins. I can't take anything out, so I'm going to end up with 63x squared all over 7x cubed minus 2. No matter how badly you want to cross that 7 and 63 off, slap your hand and don't allow yourself to do it. All right. This is the last step. We want the derivative of f of x, correct? So that means we want f prime of x by itself. Currently I have an f of x down here. So I need to bring it up by multiplication. Now I have to remember to replace it. F prime of x equals. What did f of x equal? That. So you can't leave it as an f of x. You have to put this whole thing down and then that in brackets. Now don't whine, because the positive is that's as good as it gets. You don't have to make common denominators or anything crazy. You just write your f of x here in a big bracket. So we're going to get x plus 3 squared, 4x cubed minus 1 over 8x squared plus 6x to the half seven x cubed minus 2 to the third, or to the 3, sorry, and then this. Bless you. So this is type 1 of logarithmic differentiation. I'm going to give you some quick